Okay, for those of you who are following along, I'm going to briefly walk through some notation and actual functions like addition, multiplication that we're going to be using and that are important for moving from bivariate to multivariate regression. And I just want to begin with the actual notation of the outcome as well as our predictors and our residuals. So the large uppercase bold Y is an indicator for a vector of observed outcomes. Again, this is just like yi. Now, instead of having one covariate, we have multiple covariates. So we're just going to basically put those vectors together into a matrix, which we'll call boldface X. Then we also have lowercase b, which is going to be a vector of unknown slopes that we want to estimate. So again, remember, because we have multiple covariates, we now have multiple slopes that we need to estimate. And then we're also going to have a vector of errors or residuals. So we can look at this in matrix notation. So y is a vector. It's going to be of length n, however many observations we have, and there's only one column. We then have our matrix of covariates where our first column is just going to be our intercept. That's just going to be all ones. Then we start with the second column, which is our first covariate, then the third and the fourth through k number of covariates. And again, this is going to have n number of rows, so the number of observations that we have. We are trying to estimate, since we have k number of covariates, we're trying to estimate k number of coefficients. Finally, we have the residuals or errors for each observation through n. So we can write our regression line as y equals, and I'll give you a second to think about this, x beta, right, because we're multiplying the x's that we observed times the estimated betas that we're trying to get, and plus our residuals. So in that previous slide, when we're using addition, we can think about adding two vectors or matrices, x and y, and when we add them together, we're just going element by element. So for x1, we're adding y1, and the result is going to just be x1 plus y1. That's pretty simple. The same will hold for subtraction. So for each element x, we will subtract each element y and have the resulting x1 minus y1. Things get a little bit trickier for multiplication. So when we have two vectors or matrices, we have to make sure that the dimensions are going to be compatible. So in this case, when we're multiplying A times B, we need to make sure that the number of columns in A is equal to the number of rows in B, and this will make sense in a second. The same could be said if we have B and A. Again, we have to make sure that the number of columns in the first matrix is going to be equal to the number of rows in the second one. And the resulting matrix that we're going to end up getting then is going to be n times q or m times b. We can briefly walk through an example where we have x times y, and x can be 2, 0, 1, 5, 1, 3, where we again have three columns. Y then is going to have three rows in order for us to do matrix multiplication. Once we do that, then we can actually see that we're going to get a resulting matrix of, again, 2 by 2. And I want to briefly walk through one cell in case you guys have forgotten how to do your matrix algebra. So for us to solve this top quadrant here to get 2, we do 2 times 1 plus 0 times negative 1 plus 1 times 0. which again, these cancel out and we end up with just 2 times 1, which is 2. Now, that's really complicated. I won't expect you to ever do that by hand, and R is really great. We can actually do this in R quite easily using this percent multiplication percent sign, which again is matrix multiplication in R, but you have to make sure that everything comports because otherwise you're going to end up getting a funky answer. But you can see that I put in our example X and our Y. I use the matrix multiplication in R and I get exactly the answer that we would have gotten when we calculated it by hand. Another useful function that will be kind of calling quite frequently when we actually end up doing the matrix algebra to estimate the best linear line by hand is to transpose a matrix. And so essentially what this is doing is just kind of rotating it. So if we have a 2 by 3 matrix and we take the transposition of it, we're going to end up getting a 3 by 2 matrix, as you can see here. Now we can easily do this in R by just doing T and our matrix X, and we get the resulting matrix that we would if we had done it by hand. So another really useful function that we'll make use of in a couple of slides is multiplying a matrix by its inverse so that we end up getting just 1. And first, we need to find what an inverse is, and we can do that in R by using solve. And so an example that we'll use in a couple of minutes is taking X transpose X by its inverse and then multiplying that by X transpose X. This gives us an identity matrix, which is essentially just a matrix where we have ones along the diagonals and zeros along the off diagonals, right? So this is going to be like a fancy trick essentially that we use when we're creating our estimator using matrix notation. But anyway, you can see here that if we have our matrix X, and again, we take transpose X times X and take the inverse of that multiplied by transpose X times X, we end up getting an identity matrix.